So unconventional liquidity concentrations. This is largely a talk on AMMs. I'm going to cover primarily three ways of concentrating liquidity. Constant product, kind of like hyperbolus you see with EulerSwap. Constant sum, which is x plus y equals k. And a slightly different one, which are concentrated circular market makers, where you use circles. So in general, one way of concentrating liquidity is with Riemann integrals. Basically, you have a series of liquidity boxes. Actually, let me put a full screen. So in the top right, you see there's a QR code, and for each method, you can just scan it, and it will give you present. There you go. Okay. So in the top right of each slide, there will be a method, and we'll show you how each one of these is done. So in the first case, I use a Levi distribution. That's a fat tail distribution, and I match a series of LP positions in order to optimize liquidity for them. So here's a very basic example of how to use it. So it kind of does all the math for you. You have a particular forecast, let's say Ethereum or whatever it is, and then the sum of those LP positions gives you a certain payoff. What you can then do is you can also borrow a certain amount of ETH, and it will optimize for the LP position. In this case, it tells me I should borrow 32% of ETH. And it takes about 13 seconds for the math to be done, and it should optimize it. Yeah. Let's see here. Yeah, I guess the computer's kind of slow thinking, but so I'll just move on. So in the second point, what you can also do is concentrate liquidity in a convex manner. So what does this mean? It means you provide less liquidity in the middle, but then build it up on the edges. In this case, what you get is a certain different kind of LP payoff structure, which is largely in the middle, you have a limited amount of impermanent loss, but then on the corners, you have a large drop-off. So this is a kind of a convex liquidity mechanism. So, okay, and here's the first example. You can see that by borrowing a certain amount, we kind of flatten it. Here's the same concept. Here the regression tells us that we should borrow 11%. So if we borrow about 11% right here, we're largely flat. So most of the time, we'll delta neutral, but on the edge cases, we will see massive increases in impermanent loss. Now, a third method is a very interesting one, and this involves overlapping partitions. So for example, whenever you have an LP position that is concentrated in the top left, usually it's rather narrow. But sometimes what may happen is, what if people want to borrow LP positions that are wider in range? And so what you can do is that with this method, you have multiple fixed width positions that you overlap one over another. And as you can do that, so for example, if you use this position, kind of like the previous Riemann integral cases, you can have something like the red payoff. But if you use these wider ones, what you can do is you can overlap them, and you can have the same liquidity, only in wider ranges. Why is this useful? Well, you will still be able to earn fees, but you can now lend out the wider range liquidity, because that might be more in demand. So some people might be more interested in this kind of a payoff instead of a very narrow one. At the same time, there's also another way of concentrating liquidity. And so instead of using constant products, kind of like with EulerSwap, you can use constant sum. So you use a series of straight lines to mimic or come close to mimicking a particular kind of curve. So in this case, we use 3 straight lines, and then the conditional statement to switch between them. So for example, here's an example. Let's say you come up with a certain payoff. Let's see if it loads. Yeah, let's say it's a very, very complicated payoff. You're like, I want this kind of a payoff. Well, if you were to take a swap function, in Solidity, it would be not possible to replicate it. But what you can do is you can use a series of constant sum market makers, in this case, in the blue lines, that will roughly approximate it. There's also another kind of aspect to constant sum market makers that I've hacked on with FHE. So for those who don't know, FHE is fully homomorphic encryption. It allows you to perform computation on encrypted variables. The way that this is useful for us is whenever we do swaps, we perform a certain amount of math. Well, when the transaction goes into the mempool, what you could do is you could encrypt the swap function. Then as it passes through, you can then decrypt it. And so an interesting question is, what is the minimum amount that we can encrypt? And you can create, for example, a simple Boolean value that you can encrypt, which is, are you swapping X for Y or Y for X? Are you buying or are you selling? And encrypt the quantity, in which case you kind of put the person trying to rearrange the transaction in a very kind of strange place. It's unpredictable as to what you can do. The issue with FHEs is very computationally expensive, so one workaround it is to avoid division. For example, the problem with the constant product market maker like this one is it requires division in the swapping function. But what you can do is you can usually use constant sum market makers like this one. And so in this case, you actually avoid division as you switch through. So that's kind of FHE. Another slightly more complicated topic is what you can use constant sum market makers for is you can estimate power laws. So let's say, let me just give a brief example. In this case, what we are looking at is the tail of DAI, USD. So, but we're looking at it in log-log. So let's say you have a simple distribution. But now if you were to look at it in log-log, what you do is you make the y-axis in log and then the x-axis in log. And so what you're looking at is the tail of how liquidity drops off. And so an interesting pattern here is, for example, for DAI, it drops off kind of like a power law, but then it also has like a certain sinusoidal variation inside it. And so an open question, at least in the liquidity optimization space, is it possible to express a sort of a sinusoidal pattern in liquidity? So far I haven't seen one yet, but I think it's an open problem. So for example, you can see with DAI USD, right around the 10 to the -1, which is like 1%, you have a certain unusual kind of this phenomenon, which is like when the mint and burn functions are implemented for DAI. And you can also see the same phenomenon if you were to run a tangent along this space. You would see that there's a little bump right there. And so what you could do is you could actually construct a certain liquidity distribution that is not just like one giant wave, but a wave with two additional ones. I so far haven't seen anyone do it. You could kind of use the EulerSwap V3 method that I've shown, but maybe it's possible to do it just as a custom curve. And so here's kind of an interesting example that I'm going to talk briefly about with Euler. As you might have heard in the news, Euler recently released its own AMM called EulerSwap. But intriguingly enough, before they released it, they had a certain prior version to it, which is a very, very interesting one. So they did not go with this one. But this one happens to be a rather unique function in the sense that in log-log, kind of like this one that we've shown, it has a certain alpha that it largely keeps flat, largely an alpha of 2. So in this case, it is this little black line right here. And so as liquidity decays, it decays kind of in a parallel fashion. But they did not decide to go with this one. Instead, they actually decided to go with something like this one, like the green one. So you slightly decay, but then you flatten it out kind of like EulerSwap. So let's quickly take a look at this one. So what they did is they have a custom curve, but they split it in half. So on the front end, it kind of looks just like EulerSwap. So the blue line is just the uniform liquidity. The red one is kind of just x times y equals k. And so what you can do is you can concentrate. So far I've connected their two parameters, and you can see it kind of becomes a constant sum market maker. Its blue line concentrates kind of like a power law, but what they actually do is they actually split their liquidity. So you can have, for example, a constant product on one end, and something close to a constant sum on the other. So in this case, as the price increases, we can have something like a constant sum. And as the price decreases, we can also have a constant product. So that is kind of like EulerSwap. Another interesting trick here is you can see how its payoff structure, in this case in green, mimics that of EulerSwap. And then what you can do is you can kind of concentrate it. It's a split function. There you go. So yeah, so that's kind of like how EulerSwap works. These are the custom curve cases. Now, for another version, which is what if you don't have to like split them? What if you could have just one curve? So for example, curve.finance is precisely one such example. You might have seen recently, just yesterday in the news, Paradigm released this thing called an orbital AMM. I'm going to briefly talk about it because it's actually very similar to an AMM that I came up with about a year ago, and that is the same AMM but only in 2 dimensions. And that is actually a circular market maker. Now, how does a circular market maker work? Well, it uses circles. So you don't move along a hyperbola, but you move along a circle. So let me just, it won't let me click. So with the circle, the way it operates is with orbital AMM, they just disable it, and then you can't have negative prices. But in this case, what you can do is you can have negative prices. So you start somewhere in the middle. This is your LP payoff, and what you can do is, as your LP, as people are inserting or moving around their stablecoins, you move along the curve. But one interesting thing that can happen is you can actually go negative in price with a concentrated circle market maker. Now, this may sound strange or very confusing to you, but here's how this works, and here's what this means. Usually in AMMs, you have one person inserting a token and another person taking a token out. But when the price goes negative, actually the LP winds up not just getting one token, but also the other token. Now, this is a rather unusual phenomenon, but this does happen regularly in commodity prices, especially energy. If you might remember, during COVID, we actually had negative oil prices. And a rather recent, a more recent and frequent occurrence that we're seeing in traditional finance is the occurrence of this in electricity prices, especially. So, for example, this is the United States and California. Past 2 decades, we have more and more negative electricity prices, as well as huge spikes in the other way. And so the question is, the CCMM is an interesting model, but it can be actually expanded further, because the problem with the CCMM is that liquidity is kind of symmetric, and you can't really do much with it. And so one of the things that I did come up with is this thing called the superellipse. The superellipse is a slightly different AMM, but what it does is it allows you to extend liquidity concentrations. So for example, you can take a concentrated circular market maker, you can concentrate its liquidity, and it actually becomes a constant sum market maker, like this. What you can also do is you can push it all the way to infinity, and it actually approaches a certain different kind of AMM known as a logarithm market scoring rule market maker. At the same time, what you can do is you can also split the liquidity and make it asymmetric. So for example, you can make it something like a constant sum on one end, an asymmetric one, and something closer to a constant product on the other end. So this is the case of a superellipse. And another really fascinating property of it is, I don't know how many of you are familiar with prediction markets, but one of the unique properties of prediction markets is the LMSR is kind of the most famous prediction market, AMM, and it largely concentrates its liquidity around 50-50. And since the LMSR is actually related to the superellipse, what I have done is I've seen, okay, since the limit of the superellipse here is the LMSR right here, if we push it to a very high number, then when it comes to prediction markets, one thing that we could do is we could say, okay, if we use that same formula for yes and no shares, what would it look like? And what happens is it allows you to actually concentrate liquidity around the probability. This is something that LMSR cannot do. It only concentrates liquidity as an LP between yes and no shares at 50-50. With the superellipse, what you're allowed to do is you can actually concentrate, let's say, around 60 or 70 or 10%. This is actually what you really see in the real world when you go to like polymarket and stuff like that. Most of those cases are not 50-50, and you as an LP don't really want to provide liquidity. Instead, you're forced to use like centralized limit order books. So yeah, so this is actually another way to use a decentralized approach with AMMs to concentrate liquidity around certain probabilities in prediction markets. So yeah, so that's it about the superellipse. Thank you. Yeah. Lots of information. Sorry about that.
Vasily, can I ask a question?
Sure.
When you had the circle that can have any number of collateral assets,
Yes.
And then you shifted it and it turned into a square.
Yes.
Why did it turn into a square with 4 points? Is there 4 tokens in it?
No. It's yeah. So it's just an extension. So you can actually disable them. For example, the orbital AMM that kind of Dave White wrote in Paradigm, they just disable the negative prices. So all you see is just one side here. Let's see here if it works. Choose content, start mirroring. All you see is just one end between the X and the Y. So let me show you. Yeah, there you go. So all you see here, when you push it to a value like 2, let's say, yeah, constant sum, right? But you can change it and you can just disable it. So what?
It's really one curve and another curve, and it's the 2 curves together and how many you want.
Yes. So you can control kind of how you want to concentrate the liquidity. So in this case, there's actually like this blue thing right here, the blue distribution that shows you how liquidity is concentrated. you can always disable negative prices. And so what does it mean when it wraps around? So this is an interesting case. This is a case of what if you have two assets and both of them can go negative in price? So this isn't something that you can do in TradFi. A funny example would be, for example, oil and natural gas. Both of them are byproducts. Well, there may be a case where both oil goes negative and natural gas goes negative. And say the price of oil is negative $4 and the price of natural gas is negative $2. And so what will happen is you can actually keep going along the circle and you will wind up like on this side right here. So you wind up, because you're still able to trade those two tokens together. So you can actually go around the circle. Actually, here's an interesting kind of mathematical concept that many people don't know, but EulerSwap actually also has negative prices. The problem is that they are unreachable. You see this is a hyperbola, but what you can also see is in the bottom left, there's also another one over here. And so the way that works is a hyperbola actually does go all the way to infinity, but then it wraps around you. The problem is the price can only go to 0.00001 or something. And so it never crosses into the negative domain. And so as more and more real-world assets are tokenized, you will be bound to run into a situation where at least one of those assets is going to be negative in price. And in that situation, you're kind of in a peculiar world because then the LP becomes the person on whom you can actually offset your asset. You could mint the asset in the real world and then sell it to the LP at like 0.001. So it's an interesting exploit. And so for that case, you might want to have like a negative price AMM in the future. Yeah, hopefully that helps. Any other questions? All right, thank you.